In this video, we're going to look at how we can use a simplifying assumption to bypass the quadratic in order to make some of our equilibrium calculations more simple. Here we have an equilibrium of ammonium in solution breaking apart into ammonia and H+. This is part of a weak acid dissociation. This is something that will be dived into deeper in acid and base chapters in other courses. But what we need to know here is that the equilibrium constant for this dissociation is 5.6 times 10 to the minus 10. If we think about our mass action expression, it's going to be the ammonia concentration. It's going to be the H plus concentration divided by the ammonium, the NH4 plus. Our products over our reactants. If at equilibrium, this is equal to something times 10 to the minus 10, we must have very little on top and a great deal in comparison on bottom. What this tells us is that this reaction does not happen very well. The vast majority of our cations stays stuck together. Let's figure out just how much does break apart. Let's say I make a solution and I add half a mole of ammonium chloride to 1 liter of water. Well, ammonium chloride will break apart into ammonium and chloride. It's the ammonium that we're looking for. So initially, if I have half a mole per liter, then I have 0.5 molar. So we'll do this in 1 liter, which just means I have that half mole. So I have a half mole of ammonium. We're putting in a half mole of ammonium chloride. There's a half mole of ammonium there. And I'll have no products to begin with. There's going to be some change over time. Well, all I can do is the forward reaction, so I must lose some starting material, I must gain some products. This will eventually reach equilibrium, and I'll have half a mole minus some amount, and I'll have that amount of my products. If we wanted to solve for x here, we would have that our K is equal to our ammonia, x times our H plus, x, all over our ammonium, NH4 plus, of 0.5 minus x. Since we're in 1 liter, it's just the moles divided by 1 to get our concentrations. Well, we know our K value, that is 5.6 times 10 to the minus 10. I can multiply the bottom part over, rearrange a little bit. We'll find that 2.8 times 10 to the minus 10, so a half times our K, minus 5.6 times 10 to the minus 10x must be equal to x squared, our top two multiplied together. 0 equals x squared plus 5.6 times 10 to the minus 10x minus 2.8 times 10 to the minus 10. So we added 5.6 times 10 to the minus 10 to each side. We subtracted 2.8 times 10 to the minus 10 to each side to get it rearranged. And now we can set up our quadratic. We have A, we have B, we have C. This is how we would solve this if we were going through the quadratic method. So let's do it first before we see the simplifying method. Remember that negative b plus or minus square root of b squared minus 4ac all over 2a is our quadratic. 1 is a, this is b, and this is c. It's going to give us a plus answer and a minus answer, which would give us 1.67 times 10 to the minus 5 for the positive route. And will give us negative 1.67 times 10 to the minus 5 for the subtraction route. Well, x can't be negative, so the only route that makes sense is the addition. And so x must be 1.67 times 10 to the minus 5. And if we think about our starting ammonia concentration, 0.5 minus 0.0000167, we have 0.49998. which is not a significant departure from the original amount. This is where we can make use of a simplifying assumption. We only had one-ish sig figs in this problem. Even if we'd had reliable 2 sig figs, I would have simply rounded 0.49 back up to 0.50. If the amount we're going to subtract from our starting quantities is significantly smaller than the starting quantity, then within our error, we likely won't see the difference. Even though it is, in theory, 0.49998, that would just round back to 0.5. This means that subtracted x value is so tiny that it's not going to meaningfully change our calculation if we don't include it. This would make our math come out slightly different. Here, when we set up our equilibrium expression, 5.6 times 10 to the minus 10, well, anything greater than 0 is still something, so the x for the products would still matter. But 0.5 minus x was so close to 0.5, we can just ignore the minus x. Within our error, within our sig figs, we won't notice the difference between these two values. If I do this, this simplifies my calculation greatly. I'd still multiply the 0.5 over. 2.8 times 10 to the minus 10 is going to equal x squared, which means to solve for x, I just need to take the square root now. No quadratic is necessary. When I calculate it out this way, I get 1.67 times 10 to the minus 5. If we'd had more sig figs, we may have noticed a very slight difference in x value eventually, but within the error of this problem, we don't notice a difference in x. This means that we can bypass the quadratic equation in some equilibrium calculations. When the expected value of x is very tiny compared to the original concentration, the equilibrium concentration will largely look like the initial concentration. And so 0.5 moles is still what it looks like afterwards because x is too small to make it meaningfully change. Still, anything more than 0 is a significant change, and so we keep the x for the other components, but we can ignore it for that starting concentration of ammonium. This is something we can identify from the start. We can look at our K value versus our initial concentrations. As we said at the beginning, products over reactants, with a K this small, we expect to make very little products. We expect to make a lot of reactants. And we started with reactants, so very, very little of my reactants should ever fall apart. If they do, then I won't have this small of a K value. If we'd had a very large K value and a lot of products to start with, then we could have assumed that we would have stayed mostly products. So we have to look at the reaction and the starting situation versus the K value to see if we can assume that x will be too tiny of a change. But in the situations where we can predict that changing by x will not meaningfully change the original value, we can simply ignore the x, simplifying our calculation greatly, avoiding having to do the quadratic. And as we can see here, getting the same values in this case, regardless of which method we undertook. How far can this be true? In general, as long as the initial concentration divided by the K is greater than around 400. When that ratio starts to get smaller, this means that K becomes a reasonable amount versus our starting concentration, and therefore our products produced will use up a reasonable portion of the starting material. The closer to 400 you are, the greater the error will start to become between the simplified versus the quadratic calculation. But if you are more than about 400 times this ratio, then the error will be so small compared to the starting concentration that we won't significantly notice it. This also has the effect that as we dilute a solution to lower and lower concentrations, we can make this assumption less and less often. If we had the same initial reaction, but our initial concentration was something like 5 times 10 to the minus 4 instead of 10 to the minus 1, which was our original. K does not change. K is still 5.6 times 10 to the minus 10. K is dependent only on the reaction and temperature, not on the initial concentrations. In this case, our starting concentration is much closer than the original 0.5 was. However, it still may be far enough away. 5 times 10 to the minus 4 divided by 5.6 times 10 to the minus 10, we are 6 orders of magnitude different here. This should play out far more than 400 different. And if we calculate it out, we'll find out that it is a ratio of 892,857. So this is still far greater than 400. We could still make the simplifying assumption even using a 0.5 millimolar solution of ammonium. But if we compare that to the original 0.5 divided by K, we'll find that it was originally 8.928 times 10 to the 8. As our concentration of ammonium got lower, our ratio between that concentration and the equilibrium constant grew smaller. Eventually, our concentration will be so low that we can't use the simplifying assumption. If we think about why for a moment, well, the idea is that we don't need a very large amount of product. In fact, we need very little product. However, when we had a large amount of starting material, very little product versus a large amount of starting material doesn't meaningfully change the amount of starting material. But as I have very little starting material, removing even a little bit of it to make product effectively is removing a fair portion of it. And so as the amount of starting material is less to begin with, taking that same small amount out of it is a bigger proportion. Taking 10 out of 1,000,000 is very small. Taking 10 out of 100 is much more significant. And while the balance will change slightly, as this is equilibrium and the ratios are what we are concerned about, the net effect is that as our initial concentration gets smaller and closer to the K value, our ability to make this assumption goes away.